Hello, this is Metallo E-Lab. My name is Professor Chuka Nwoye, a professor of regenerative chemical process evaluation and empirical modeling. Today, we're going to talk about leaching of lead zinc ore. Lead zinc ore contains some pockets of zinc and chalcopyrite in form of sphalerite, chalcopyrite, galena is also involved. And so this process was carried out using butanoic acid solution. And during this process, several results we obtained, several data, experimental data were realized. And these experimental data were used to derive the model, as you can see in the screen. The essence of this work is to extract zinc from the whole lot of lead zinc ore. Here, alpha is the initial solution pH. The gamma is the final solution pH. And then you can see the concentration of extracted zinc measured in the milligram per kilogram. In order to make the model to work effectively, there are some empirical constants available. And you can see from the screen, one of them is 1.4, the other one is K, it's 1/3. We want to go into problem solving to see how some parameters from the work can be juggled and the unknowns found with the help of the known. Now, in model 7, it says calculate alpha if gamma is 4.3 and the extracted zinc concentration is 75.2. In other words, we are looking for the initial solution pH in this work, since the final solution pH was given. Now, if we substitute all these values into the model, we're going to have initial solution pH to be equal to 1.4 multiplied by the final solution pH, which is 4.3, divided by natural log of, in brackets, 75.2 to power 1/3. Now, if we evaluate the cube root of 75.2 from equation 1 in order to get a simpler value, we're going to have that alpha will be equal to, that is, the initial solution pH will be equal to 6.02 over natural log of 4.22. And in this particular equation, you can see that the value of 1.4 was multiplied with 4.3 to get 6.02. Still solving, if we evaluate the natural log of both sides, now we're going to have, if you evaluate the natural log of 4.22, we're going to have 6.02 all over 1.4398. And the alpha, which is the initial solution pH, will give us 4.18. In model 8, it says calculate. Now, in this case, we are looking at the final solution pH if the concentration of extracted zinc is given and also the initial solution pH is given. So if we substitute these values into the model, we're going to have 3.6 is equal to 1.4 multiplying the final solution pH all over natural log of, in bracket, 81.4 all to the power 1 over 3. And if we, in order to remove the bracket below 1.4 final solution pH, we need to first of all evaluate the cube root of 81.4. And in doing that, it's just a way of simplifying equation 2. And when we do that, we're going to have that 3.6 is equal to 1 over 4 multiplied by the unknown, which is the final solution pH, all over natural log of 4.33. And if we evaluate the natural log of 4.33, we're going to have 1.4656. And this will give us 3.6 multiplying by 1.4 multiplying by the unknown final solution pH all over 1.4656. Now, since 1.4656 is dividing 1.4 multiplying the final solution pH, if we multiply both sides by 1.4656, the one that is below 1.4, the final solution will be cancelled out. And so we're going to have 1.4 multiplying the final solution pH to be equal to 3.6 multiplying 1.4656. And invariably, we're going to have 1.4 gamma to be equal to 5.2762. And with that, we can find the final solution pH to be 3.77. In model 9, we want to calculate one of the empirical constants when the other one is given. Now we are calculating this empirical constant when K is 1 over 3. The final solution pH is 4.67 and the initial solution pH is 4.65. While the quantity or the concentration of extracted zinc is 67.96 milligram per kilogram. Furthermore, if we substitute these values into the model, we're going to have 4.65 to be equal to empirical constant multiplying 4.67 all over natural log of bracket 67.96 to power 1 over 3. And if we evaluate the cube root of both sides of that equation 1, we are going to have, if we evaluate the cube root of 67.96 to power 3 to be able to have a simplified figure, we are going to have that the cube root of 67.96 to power 3 is equal to 4.081. And so, getting the natural log of in log of 4.081, that's finding natural log of the value, we're going to have 1.4063. That will give us equation 2. And then, when we simplify further, we'll have that multiplying from equation 4.65 by 1.4063, we're going to have on the right hand side 6.5393, multiplying to be equal to the constant multiplied by 4.67. And with that, we can get the constants, the empirical constant to be equal to 1 over 4. This agrees with the model, where we have the only constant on top of in the model to be 1 over 1.4. So this agrees with the first principle model. In model 10, it says calculate K if the other empirical model 1.4 is given. Here the final solution pH is 4.69, the final solution pH is 4.68, and the zinc extraction concentration is 70.01 milligram per kilogram. If we substitute these values into the model, we're going to have 4.68 to be equal to 1.4, multiplying the final solution pH, which is 4.69, all over the natural log of brackets 70.01 raised to power k, which is the unknown empirical constant. Now, to be able to simplify this model at this juncture, if we multiply both sides of equation 1 by natural log of bracket 70.01 to power k, if you do that, you will find out that the value of natural log of 70.01 k below the product of 1.4 and the final solution pH will cancel out, and so we are going to have natural log of bracket 70.0.1 to power k multiplied by 4.68, which was already on the left hand side, to be equal to the product of 1.4 and the final solution pH. Now, evaluating the right hand side of equation 2, we're going to have, when we multiply 1.4 by 4.69, we're going to have 6.566. And then, if we divide both sides by 4.68, remember that in equation 3, we have 4.68 by the left-hand side. And so if we divide both sides by 4.68, we're going to have natural log of bracket 70.01 raised to power k to be equal to 1.403. And so, if we get the exponential of both sides, the exponential of what we have on the left-hand side of equation 4, we cancel out with the natural log symbol, and so the other side, if you get the exponential of 1.403, we're going to have 4.0674. The next thing now will be to take log of both sides of equation 5, because the essence of this is to look for a way to evaluate k, which is the unknown. So when we take the log of both sides of equation 5, we're going to have log of 70.01 to power k to be equal to log of 4.0674. Now, if we rearrange this equation 6, we bring down the k that was formerly in power form. It becomes k multiplied by log of 70.01 to be equal to log of 4.0674. This is in line with the law of logarithm. Now, evaluating both sides, the log values of both sides, we have 1.8452k to be equal to 0.6093. And so k will give us 0.33. And if you look at this, this also agrees with the value of k from the model. The value of k from the model is 1/3. And if you divide 1 by 3, you have 0.33, approximately 0.33. So that shows that it agrees. Our problem solving has, we have gone back to what we have in issue. We have been able to get what the model portrays in terms of the empirical constants. Now, in model 11, we want to calculate the concentration of extracted zinc when the initial and final solution pH were given. And in some manner, if we substitute these values to the model, we have the initial solution pH to be equal to 4.83 to be equal to 1.4 multiplied by the final, which is 5.35, all over the natural log of the extracted concentration of zinc to power 1/3. And if we multiply both sides by the natural log of the concentration of zinc removed to 1/3, in order to cancel out the same value that's dividing the right hand side, we're going to have what we have on the screen, and that will give us a natural log of the concentration of zinc removed to power 3 multiplied by 4.8 to be equal to 1.4 multiplied by 5.35. That's exactly what we're going to obtain. And so further evaluation will give us that the right hand side, on evaluating it, will give us, on multiplying 1.4 by 5.35, we're going to get 7.49, being equated to the natural log of extracted zinc concentration to power 3 multiplied by 4.38. And when we do that, we're going to have that in order to eliminate 4.38 from the other side and be able to get the unknown, we divide both sides of equation 3 by 4.83. When we do that, we're going to have natural log of extracted zinc concentration to power 1/3 to be equal to 1.55. Now, the next thing to do is to get the exponential of both sides of equation 4. And when we do that, the exponential sign will cancel off the natural log value ab initio in equation 4. And we'll have the extracted zinc concentration to power 1/3 to be equal to 4.71, which is the exponential of 1.55. Now, in order to get our value, the extracted zinc concentration, what we do need to do now is to cube both sides. And when we do that, according to law of indices, the power 1/3 to which the concentration of removed zinc is raised will cancel out, and 4.71 will be cubed. And when we do that, the value of the concentration of removed zinc will become 104.49 milligram per kilogram. It is important to take note of the fact that in this process, it has become an occurrence that the final solution pH is always greater than the initial. Let's go down and look at the model 10. Look at the final solution pH is 4.69, while the initial solution pH is 4.68. And when we got the value of, when we did some calculations and got the value of one of the pH values, you can look at this. You see that when the final pH solution is 3.77, the value of the initial was 3.6. So you can see that the final is always greater than the initial. And what does it mean? What it means is that at the end of the process, it is believed that a reasonable part of the hydrogen ion must have been exhausted at the end of the leaching process, and so the pH will move up a bit. I want to thank you for listening, and I want to enjoin you to look at the source of this work. This is the source of this work. You can look at it and see some experiment, the way the experimental work was carried out, the way the model was derived, the deviation, and all that. Sincerely, I want to thank you again for being part of this model and studying and part of this discussion. I'm still your instructor, Professor Chuka Mui. Please don't change your channel. It's still Metallo Maths E-Lab. Thanks for watching and goodbye.